Hi, this is Dr. Simon Romero. I'm here to present you the video tutorial for double integrals over polar rectangles. First, let's talk a little bit about polar coordinates in R2. The idea is, in R2 you can describe a point by two numbers. The two numbers can be how much you move in the x-axis and how much you move in the y-axis, and those are called rectangular coordinates. And then we can also describe it by taking just the line segment from the origin to the point and describing what's the length of that line segment that I'm going to call R, and the angle that that line segment makes with respect to the x-axis, and that's going to be theta. For polar coordinates, these are the formulas that we use. Actually, we are going to mainly use the first three. Now, why we're going to do that? Because polar rectangles are going to be important for taking double integrals over those regions, and the reason is because they are what I would like to call integral friendly, and I'm going to tell you what does that mean in just a moment. So a plane region R is a polar rectangle if this happens. So if in polar coordinates it does look like a rectangle, the R moves between a number and a number, and the theta moves between a number and a number. What do they represent geometrically? Geometrically, they are not going to look like rectangles, but they are going to look like sections or little pieces of a circle. So, for example, in this case, we have that the R is moving between two numbers A and B. So these are the two numbers, and if you take all the points that have R between A and B, you will consider all the points that are in between these two circles right here. And then when you restrict your angle theta to be between alpha and beta, are all the points that are between those two lines that pass through the array. So at the end, the thing that we have is this is a polar rectangle. So why we need to talk about polar rectangles? Because actually that we're going to do our approximations or our Riemann sums using polar rectangles. Let me just explain you what's going on. Recall the definition of double integrals over rectangles. So the thing that we're doing is we are approximating, in this case, the volume under the surface by using boxes with rectangular bases. That's kind of like the idea. So the question is, well, can we change the region to be something else? And when we were doing it with rectangles, the thing that we needed in order to construct these boxes, we used two things. We use the area of the base, that in this case is just delta x times delta y, and we need the height, and the height is given by choosing a point in the corresponding small rectangle. And then you just take to add all the volumes of the boxes, and then you take the limit. So we need to know how to compute the area of our polar rectangle. First, we're going to do exactly the same thing. We're going to subdivide the interval of the radius and the interval of the angle. And with that, we're going to create the smaller polar rectangles, and from there, our boxes are going to go up to the surface. So in order to compute the area of R, that's what we need. We need to compute the areas of polar rectangles. We need to do the following. We first compute the area of this section of the disk. In this case, I'm calling S2, and then we're going to subtract the small section of the disk, the area of the small section of the disk, that I'm calling in this case S1. So the area of the S2 is equal to this, 1/2 b squared delta theta. The reason why is because we're considering our measure of the angles in radians. So the area of the section of a circle is given by this. The area of S1 is the same, but with A instead of B. And then we're going to subtract them, and that's what we get. Now, if we factorize the expression, the thing that we get is this, and we can factorize even a little bit farther using this factorization, and the thing that we're going to obtain is 1/2 b plus a times b minus a delta theta. Now, b minus a is actually the difference in the radius, and 1/2 b plus a is actually going to be the average radius. So the thing that we're saying is the area of R is equal to the average radius times delta R times delta theta. This is going to be very important, and you will see how this average radius that I have right here is placed in our formula for computing double integrals. So now we're ready to understand double Riemann sums in polar coordinates. So the thing that we start with is with a polar rectangle. I'm not going to draw the function. You can imagine that the function is above this polar rectangle. So we start with a polar rectangle. Then we subdivide the radius interval into subintervals of the same length, and the length is going to be delta r. We do the same for the angle interval, so all the intervals are going to be delta theta. And the thing that we obtain polar rectangles, that we subdivide the big polar rectangle into smaller polar rectangles. So we pick a sample in each one of the smaller polar rectangles, and this is the area right here, the area of those rectangles. It's going to be the average radius and delta r and times delta theta. Now I'm going to pick these particular points that are the points where r star I is just going to be the average radius of that particular polar rectangle, and theta j star is just going to be the particular average angle in each one of these polar rectangles. So the thing that we have is when we multiply by the particular sample point, this expression gives us, and we multiply by the area, gives us the volume of the boxes with each of the smaller polar rectangles as a base. So from each one of these polar rectangles, you're going to have a box that is coming out of the screen. Now we change everything into polar coordinates. Notice that in the expression above we have x's and y's and r's and thetas, and we're going to change everything into r's and thetas. Then the thing that we have is the double integral can be approximated by the sum of the volumes if you subdivide your intervals sufficiently in very, very fine pieces. What does that mean formally is that we take the limit when n goes to infinity, or the number of subdivisions that you take, and you add all the volumes of these approximations, and that gives you the double integral of the function. So so what does that mean in terms of the formula? Again, we're trying to get something a little bit less complicated than just computing the limit of a Riemann sum. So let me just explain a little bit further what does this formula means. So if we consider a function g of r theta, so it's a function of two variables, r and theta. Forget for one moment that we're talking about polar coordinates. You have a function that has two variables, and it's given by f of r cosine of theta, r sine of theta, r. So we know that if for some reason these are just two random variables, the r is moving between a and b, and theta is moving between alpha and beta. So these are two variables that, if we consider them as just normal variables, not the ones that represent polar coordinates, by Fubini's theorem we know that the iterated integral is actually equal to its Riemann sum. But now the Riemann sum of these things is the same as the Riemann sum that we have here over the top. So the thing that we're saying at the end is if we can take the iterated integral with respect to this function g. Notice that the only difference between what we have right now and what we had before is this extra r right here, and we will see that also appears here, and you will see how that extra r plays a role. So in the rectangles, the area is given by delta x and delta y. In polar rectangles, the area is given by delta r, delta theta, and you add the extra average radius. This average radius is the one that is going to reflect in the formula. So notice that the formula is just this formula of change of coordinates. The only thing that it's saying is that you can use Fubini's theorem as long as you change the x, you change the y, you put the limits of the x and the y, but also you need this extra r that we have right here. That's the extra thing that you have to do, and this is done because of the change of variables. Let me give you an example. Suppose that I want to evaluate this double integral. So the region is the quaternion annulus given by this equation, and x and y greater or equal than 0. So we have that these are two circles, one centered at 0 of radius 2. That's when you have the quality this way, and when you have the quality in this way, you have the circle of radius 4. Then the thing that you do is you are just considering the region that is in between those two circles, but is only in the first quadrant. So in polar coordinates, this is the way that this rectangle looks like. So remember, the change to polar coordinates says the following. You have to change the x and the y. So replace these by x and y in the function, and then add an extra r dr d theta. So we're going to do exactly the same thing. We're going to change r cosine of theta for x, r sine of theta for y, and then instead of the a, we're going to put r dr d theta. We're going to put the limit of integration, the one with respect to r, and then the one with respect to theta. So this extra r is very important. Please always remember it, otherwise your result is going to be wrong. So the thing that we're going to do is, after this, I can just multiply through, so you have r squared, then integrate this with respect to r, so it gives you that. This is a constant, so it doesn't matter. Plug in r equal to 4, and subtract r equal to 2. We have that. Simplify that. Then take the integral with respect to theta, so this is a constant, and this is what you get with the integration. Then plug in pi over 2, subtract the evaluation at 0, simplify, and this is the answer that you will obtain. And this finishes the tutorial for integration in polar rectangles. Thank you very much.